So I will take you through how we work with graphs and data in passenger transport systems. And I will share with you a number of examples from work we've done in our group in the Smart Public Transport Lab. So within our transport and planning department at Civil Engineering and Geosciences, we're organized into different research groups, public transport being one of them. So it's a group of roughly 20-25 people working full-time on topics related to metropolitan and long-distance public transport systems. And Tina is also here, who is now a guest at the lab. Jay is also here in part of the lab, as well as Tao will be presenting later. So you see the contributions by some of them and others as well. Good. So first, when you think about passenger transport systems, and graphs and data, that's by no means a novelty. So here you see an example from the late 19th century, an accessibility map of the British Empire at its peak at the time. And you can see the number of days here that it takes to reach any part of the empire by any mode of transport. And of course, you can see that while you can access anywhere in Europe within 10 days, some heartland in South America, Australia, or Africa will take you up to 40 days or more. A little bit later, beginning of the 20th century, Austrian-Hungarian Empire, you can see the accessibility by rail and how it penetrates into different parts of the empire and took more than a day, that's in hours, to reach any part of the empire from Vienna, the capital. And you can clearly see the underlying corridors of a rail network. And here you have an underlying graph, right? And data, travel time used to label this graph, to create this accessibility map. So that's not novel, but it's absolutely key ingredient in any transport analysis, understanding the underlying accessibility provided by our multimodal transport networks. Well, we have moved since, that's more than a century ago now. So I will share with you some recent developments, if my pointer collaborates. Let's see, curious. You need to click the slides. Let me do it. So first, in passenger transport systems, that is not a scientific discipline in its own right. It's rather an application domain. That goes for transport as a whole as well. It does include ingredients and expertise from many different domains. And you can see those touch upon many different faculties also at TU Delft and beyond even. And in our group, I'll have to click through. Let me see. No, that's not working for me anymore for some reason. Submit there. Say again? What do I have to do?
Yes. Because this popped up. Oh, to meet.
Let's admit everyone. Yes, thanks. That's the trick. Let me go back. Yeah. So within this range of expertise, we in our Smart Public Transport Lab and myself mostly focus in these three areas: operations research, optimization, simulation models, resource allocation, network modeling, both in terms of topology as well as network assignment models. So forecasting the distribution of flows in transport systems. And to do so, you also need to have an understanding on the behavior. Because unlike, say, telecommunication or water management systems, in transportation, people, individuals are making choices independently, in the sense that we are autonomous to make choices based on the information we have. At the same time, we're also interdependent. So we may make different choices depending on how others make choices. So that requires some behavioral science as well. So typically, the combination of these makes things interesting. So that's where I focus on anything ranging from strategic long-term planning, say of metro network development, for more tactical planning of scheduling and routing, capacity dimensioning, to real-time control decisions. And doing so for systems at different scales, from shared mobility, micromobility, to urban, regional public transport systems, up to long-distance air rail kind of transportation. And to do so, you do need to have these ingredients from networks operations and behavior modeling. So in the remaining of the presentation, I will structure it based on really these three domains in terms of scales, because we do have some consequences for the kind of graphs and data that we are interested in using. I will start with the classic, and also the kind of core activity of our group, which is metropolitan, regional, line-based, schedule-based services. In other words, what you tend to think about when I say public transport, I think, as opposed to passenger transport, which then also includes mobility on demand. That would be the second topic. Think ride-hailing, ride-sharing, Uber-like, shared fleet services. And then I will finish with the topic of the new project that was mentioned, ERC project, which is about to start on long-distance travel. I'll already give some hints on that. All right? Feel free to jump in. No need to wait or be too formal about it. Okay. So let's start with public transport services. First realization we need to have is that we have different kind of underlying networks of interest in the public transport context. This is a typical map you see at the Dutch railway stations, right? Which tells you how stations are connected to each other, stations being nodes, and the links imply that there is a track, right? Connection running between them. This is useful to an extent. I'll argue this is much more useful, but much less commonly shared. That is from the current line planning. And for the same underlying infrastructure, we can have different line planning. And every 5-10 years, that's actually updated by the Dutch railways. So here you see the different lines shown represented in different colors. You can also have the thickness corresponding to frequency if you wish. And this is more informative, of course, because here you cannot tell whether you will need to transfer along your way or not, right? So there is no way to know from any station to any other station whether you have a direct connection or where you may have to transfer. Whereas here you do have this information, but this can be overwhelming, right? Hence, this is the one which is publicly shared. But in public transport, we absolutely need both. We need the underlying infrastructure, sometimes even greater detail. And we do need the service planning, which is superimposed on that, right? And we also may label them differently. Typically, we do. So a typical label here would be the travel time or kilometers or anything of this type on the links between stations. And here we will probably also want to know something about the frequency, which has consequences for waiting times, right? Or even a time-dependent graph representation for the full schedule. So before moving forward, I will need to introduce several, so to speak, spaces or graph representations in public transport which are commonly used. They're known by their letters, and they originate from Polish. I found out after quite a minute investigation. Most people don't know where they come from. But therefore, I will also use a name which I find informative. So the first one is the infrastructure space, so to speak. That's typically the most intuitive one. Basically, you look at the map and the stations correspond to nodes, and you connect stations if there is a direct track connection availability between them. It can be hypergraph. Typically, it's not. So you typically remove when you have duplications. This is the one I just mentioned. So this will be the outcome for this one. Sometimes you may also remove intermediate stations because they can inflate or really skew a lot of indicators, and they're not very important. You can add 20 in between, right? But it doesn't fundamentally change the topology. So therefore, you often will remove those and keep only terminals and transfer stations, because those are the places where you can have a choice as a traveler route choice. So this is the infrastructure space. Then we have the service space, which is, again, still nodes corresponding to stations. So it's the same set of nodes. But now we connect any pair of stations between which there is at least one direct line calling at both stations. So that means that we now get these fully connected graphs between stops along the same line. So we get the red line and the yellow line and the blue line. And again, we may remove duplicates. And this is very useful because this we can use to tell how many transfers one needs to get from A to B, unlike the previous one. So far, so good. Then we have the transfer possibility space, as I like to call it. That's basically the dual graph of the first one. So that's where now lines are nodes, and we connect any pair of lines between which there is at least one shared station. And in this case, that's a simple fully connected graph because all lines had at least one shared station. And finally, we have a so-called B-space or transfer journey representation, where we now have two sets of nodes, both lines and stations, and we connect a line to all stations at which it calls. And so stations are connected to lines and lines are connected to stations, but not to each other. And this is the most informative one. This is also the one typically used in journey planners, because here you can tell not only that you need to transfer, but also what sequence of lines you may have to take and at which station you will need to transfer. So here I can tell that to get from A to G, I may take line 1 and then transfer at C, D, or E to line 2, or I transfer at F to line 3, right? So this contains the entire itinerary information without the time-dependent part, right? Yet. So those is that one graph used in the previous slide. The previous one, seldom, I have to say. But if it is used, it's really to look into what happens, for example, if certain lines are due to maintenance works are shut down, right? This kind of interventions. Yeah. So those are the 4 graph representations I wanted to share with you before moving forward. Are we good on those? Yeah. Let's get a little bit of a feeling for it. This is a Buenos Aires subway system. Very simple graph with basically the main kind of line cutting through the CBD, the north-south line, another one here, and then most of them really running under the main avenues to connect to those. This is how it looks in the P space. In the L space, the infrastructure space, and this is the P space. So we get these sub-graphs of fully connected graphs of the individual lines, and then we get these transfer stations which serve as bridges between them. Here is for the Washington, D.C. Metro, which is also small, but contains several cycles, so that makes it interesting. And this is how the infrastructure space, the service space, and the transfer journey one, the last one we saw, look like. All right, so that's what we use commonly in both education and research in public transport network analysis. And here is a recent work by Tina, which I would like to share with you some highlights from, which is how we can use these graph representations to also analyze accessibility in terms of different thresholds. So as you can imagine, you may have heard of a notion of a 15-minute city, of a 30-minute city. So the idea that you want to provide certain level of accessibility to all residents. And you can simply take these graph representations and establish different thresholds in terms of travel time budgets, so to speak, and look how that affects the number of destinations one can reach from any origin in the network. And as you can see clearly, of course, once you increase here with 2 minutes increments, the graph becomes much more dense. And we can use this to compare different networks and understand what are the typical patterns in terms of accessibility provided. Here is just for the simple example of the Amsterdam Metro. We also did so for 8 light rail systems from different cities. You can see from Melbourne to Budapest and Amsterdam among those. And here we included information from both L space and P space. In other words, both the infrastructure as well as the service layers. And if we do so, we get something which we call in transport generalized travel cost, which is basically that you weight different travel time components based on how those are negatively perceived, because we always want to minimize our travel time. So typical value that is used is that any minute that you have to walk or wait is perceived as negatively as twice as negatively as the minute that you spend on the vehicle. So then we take this weighted average travel time using information from both infrastructure space, which is the travel time, as well as the service space, which is number of transfers and waiting times. Transfers are particularly disliked, right? And the typical transfer penalty, as we call it, so how negatively you perceive a transfer, is an extra 5 minutes travel time equivalent. And if we do so, then we get this function that we can then look how it looks for different networks. Of course, larger networks are in a way penalized, right? So that's the Melbourne tram network, which is the largest in the world. Also experiences much longer travel times. This urban agglomeration is also geographically much larger, not only many more stops, as opposed to, say, the Amsterdam one or the Zurich ones. So it's not only an indication of the quality of a network, but also has to do with the size. And that's something we do try to control for in some of our studies. I will get back to that. So this is on the supply side of things. The topology, right, of a network and accessibility that it offers. For this, we don't need to know anything about how it's actually used, but simply the service that we offer. But well, ultimately, you are interested in how people use our systems. And from several systems, we do have access to very detailed disaggregate smart card data, like in the Netherlands, right? We have to tap in and tap out. And we can use this to understand how people make choices in public transport systems. And in this study from 5 years back now, we looked into how well can our topology allow us to forecast how people make choices in our networks. So what we did here, without going to all the details, is we looked into correlations between different topological indicators and the distribution of flows that we observe in the networks, for both Amsterdam and The Hague in this case. And what we found is that there is a very high correlation. So in other words, we can explain the vast majority of the variation that we see in flows in the network strictly based on two topological indicators, namely the betweenness centrality in the L space and the P space. And that should not come as a surprise, because betweenness centrality gives an indication of the share of shortest path, right, that go through a node. Well, that's how people tend to choose the routes. And they minimize both waiting times and transfers as well as in-vehicle time. So that should explain much of the variations. It does not help us necessarily say what will happen when we extend the network. Because if we build a connection to a new area, we don't know what is the new demand level that will be generated. So it's only useful for redistributing flows in an existing demand level. That has to be said. So we don't need to throw away yet our transport forecasting models. But it is useful for especially when you have temporary closures, I can imagine, of different stations and links. So then you can use it to assess a redistribution of flows that will result from it. We also use these kind of representations to understand how performance varies across the network, and in particular passenger delays. So we tend to, or used to, measure punctuality and delay mostly in relation to train arrival times, bus arrival times. But ultimately, we're interested in how passengers experience delays. So how much of a discrepancy is there between the travel time you could reasonably expect and the travel time that you ended up experiencing? And that's what we did for the Washington, D.C. network, for which we have long-standing data, both tap in, tap out for the metro system, as well as the train movements and disruption data. And we use this to basically formulate a system of equations for passenger delays. And this allows us to then estimate the amount of passenger delay, which is generated at any location in our graph. Can be a transfer station, can be a track segment, whatever may be the case. And this is an illustration from a given weekday, a given weekend day, about how delays propagate in time and space. So this is a 3D kind of graph, right, of a network, and then each slice is half an hour, and then we stack them. So that's what we see here. So for example, here we can see that something happened on this rail corridor, and it's propagated in both time and space. So delays, passenger delays, were experienced there also much later and also further downstream. And this can be useful to prioritize how to intervene, right, and where to allocate resources to mitigate delays. We use it also to understand how they propagate. And I think here maybe one of you will be also inspired to follow up on that, because I think we can do much more than we have done so far. So we did look into estimating the Bayesian network for the delays and distributions of delays in different stations. And this is the result of that. So what you see here is, for example, that delays patterns at this terminal station are very highly correlated with delay patterns here. And that is maybe looks at first a bit odd because they are not connected, right? But in fact, they are the two terminals from which you dispatch trains into this shared corridor. So clearly, if there is a delay on this line, then also dispatching from this terminal will be affected. So that's why we see. Otherwise, it's typically, as one would expect, along branches, right? They're all interdependent, but also between terminal stations here, transfer stations here. So we can analyze that and also look into basically the subgraphs which this implies in terms of how well delays observed at one station are associated with delays experienced elsewhere. So we can see that some of them are fairly isolated and also very strongly affecting each other, while we have this kind of a large component which, if a delay happens somewhere here, then it's likely to spread quite a bit. What we are missing here is the temporal dimension. I've seen some attempts, but nothing really complete. All right, so that was about passenger delay, which brings me quite naturally to the next topic within public transport systems, which is network vulnerability and robustness, which has been subject to a lot of research, also by people from applied physics and applied mathematics that use public transport systems, primarily metro systems, for this purpose. And then one of the classic studies, I think, in this field is from von Ferber. You'll see in the next slide, where they look into the tale of two cities, we call it Paris and London, of course, and comparing the vulnerability. And the question they ask is which one is more vulnerable if you are to consider a sequence of failures in these networks. And this failure can be either in random sequence, and then, of course, you need to make many simulations of which, or based on a certain order. Say that there is a targeted series of attacks on the highest node degree or the highest node between a centrality. And basically what they show is that there are large differences between the Paris and London networks in this case. So this will be the share of a graph which remains intact. This will be the share of nodes that have been removed. Right? So you start with fully connected, you end up with nothing is in place. And you can see, let's take the node degree one that's in red, that for the London network, after you removed about 20-25% of the nodes, basically nothing is left. It's very abrupt, the collapse, right? If you remove in order, based on node degree, whereas for Paris, you will have to do that for 50%. And you can see the difference also for the random one, which is in black. It's not as abrupt, but very clear difference between the London one. Look, by 50% of the nodes being removed, you have less than 10% of a graph, whereas in Paris, that's still about 70%.
What characteristic of the network makes this distinction?
So they looked strictly into the L space, so that's the infrastructure representation. Nothing about lines, frequencies, nothing like that. And also strictly topological, as in that if you remove one link, the remaining of the lines keep on operating, no demand, nothing like that. And basically, if you look at the two networks, what happens is that here, if I have to schematically represent it, that's like a grid. You see, there are a lot of ways to detour and bypass and a lot of cycles, high alpha meshiness indicator. In the London case, you have a core, which is somewhat dense, and then you have long branches, relatively speaking, and those are very vulnerable. Exactly. And I think that's not a fair comparison, because this is Paris municipality, not Ile-de-France. This is Greater London. So yeah, if you will take here, I mean, also you have longer branches of light rail, right? Okay. But this is because the metro in Paris is really for the core, and the metro in London is for the entire agglomeration. So they play a different function. That's now transport planner speaking. Anything else about that? All right. So this is kind of a dark view, right, on public transport systems and how quickly they may collapse if you were to target them. We also try to look at the bright side of things, more recently in a work on how recoverable they are. So not only how quickly they fail, that's F, right? And if we take the integral over this area, we get a measure of that, how quickly and how severely you lose performance. And here performance is defined, unlike in the study by that we saw in Paris and London, which was done by physicians. We look into loss of performance in terms of passenger travel times. So not a topological indicator, but a service indicator. So the total loss of passenger travel times. And then we also look into what happens if you, at some point, done with failing and start recovering, reintroducing links into your graph and how quickly you can recover. And we expected that this can also vary for different networks depending on their topology. So we want to minimize F and maximize R, right? And this is how it looks for all the networks we studied, about 50 of them, metro networks worldwide. We have a data set which is publicly available with different graph representations, and each curve is for a single network. So you see but they have a typical kind of behavior, but there is some variation therein. And then we also rank them all. And you can see, if you look at F, R, the ratio or the difference, depending on what you're interested in. But if we look at this one, the ratio, you can see that some of the largest networks, such as New York and London, are among the top ones, but also Santiago, which is not so large. And some of the bottom ones are Stockholm and Oslo, as well as Boston. And Stockholm is not a small network, but if you look into the topology, it has very few cycles. It's extremely radial, so it's very vulnerable and also not good in recoverability. And we also look into how these things correlate with topological indicators, and we find out that the best predictor for the failing rate is the density of the graph, whereas the best predictor for, or the best association, I should say, for recoverability is the meshedness, the number of cycles. So it's not the same thing, looking at F or looking at R, so to speak. Kind of going briefly to give you a bit of an impression. Of course, welcome to ask or look up if there are specific questions. Yeah?
This analysis can affect operation or service, because you cannot just build quickly some more lines to improve your robustness.
Right. I mean, it can affect several things. So one is that you can decide where to locate switches, so to allow you to short-turn trains, so that you can recover your service. So that's something that is more at the tactical planning level. It can also allow you to make better choices in prioritizing, say that you have limited resources, which is always the case, which lines and links you should first reestablish to gain the most in terms of performance, right? So that's where it becomes useful. And strategically, you can also try and look into where the opportunities to make the network structure more robust, right? So it's again fits to strategic, tactical, and operational decisions. Anything else? Okay. That brings me to the two other smaller topics that I want to touch upon. The first is mobility on demand, which is a very different domain within passenger transport systems. So now we move away from line-based systems, we move away from schedule-based systems. It's all dynamically determined. Much of the work there was done in the ERC starting grant, which just came to a conclusion, called Critical Mass. And for us in public transport, that means a great shift. So we don't have a centrally planned network. We don't have centrally planned schedules. Even the vehicles are not directly, they're not owned and not managed directly by the platform. We have a platform here that is a marketplace connecting customers and drivers, if you think of Uber-like services. And the routing is dynamic, the pricing is even often dynamic, surge pricing, the matching, not to mention that we also have to match not only customers and vehicles, but also sometimes customers and customers for shared rides. So a lot of interesting new problems. And some examples of the work we do in this domain. There is a lot of graph work that goes into the matching problems. Also by colleagues from mechanical engineering here. Just to give you a little bit of an impression, we can represent passenger requests as nodes and connect those if those are mutually compatible. Here we also look into the direction. So we connect if, depending on the order in which you can serve, whether you can pick up the first and then drop off a second or vice versa. And we're looking for clicks. We're looking for a large number of passenger requests which are mutually acceptable and attractive. Because if it's not attractive for you and you will instead take a private ride or you will take your private car or public transport or whatever may be the case, if you opt out, then of course it collapses for the rest as well, right? So it has to be mutually attractive, also in terms of the pricing. So that's what we do here. And of course, we know that people are not enthusiastic to share the ride, so you need to offer them a discount to do so. And that may be a function of the extent of detour or delay that they may experience. So we look into that, and they have to be mutually acceptable in terms of both time and space. And we use travel demand from data from Amsterdam to study this here. And we basically look into the extent to which we can make a request. This was also used, COVID times, remember, to study virus spreading in different networks, here specifically in shared rides. So we looked into incorporating this into basically how we form matches. So if in usual cases, this may look as a graph over days of people that you share your ride with, that might not be wise during COVID. So you may want to limit that and look into still the most efficient way in which you isolate to the extent possible matches that are made over a different number of days. So that's a bit of a kind of line of thinking that we had in this study. We also use it to, coming from public transport, to think how can we push the boundaries a bit of these services. And what I mean by that is if you start to share your ride, there is also a service by Uber, by the way, called there. So that's, there you have Uber X, which you might be familiar with. That's a private ride. There is Uber Pool, where you may share. There is also Uber Pool Express in some places, which is that you accept to also walk up to 200 meters to be picked up or from your drop-off location, which is for them useful for matching, of course, and for efficiency. And that starts to resemble public transport, I will argue. So you walk into a virtual stop, you wait, right? You share your ride, you may have to detour for someone else's sake. That's not so different from public transport, I will argue. So that's a totally private one, that's a shared one, that's the one with walk-in, and this is when we form lines based on this, basically. And lines not in the classic notions, so we don't repeat with a certain frequency, but they are formed dynamically based on the actual travel demand on the fly, but they are made for larger volumes. And if we do this again for the data we have from Amsterdam, we find that we can form sometimes up to 14 passengers being pulled together and also start to look a bit more like public transport lines, right? All within acceptable boundaries on detours and walking and all that. And if you do so, you're able to reduce quite a bit the time that people have to travel. If you do it efficiently, and particularly reduce the vehicle hours, which is the main indicator of resources use. So that shows that this is, well, mobility on demand and classic public transport, it's a spectrum, and I think there are quite some niches to fill in between. If we're good, then I will switch to the last topic I would like to share with you. Yeah, the other end of the spectrum in terms of scale. So from moving from small shared vehicles to long distance services, typically high capacity. We don't have a logo yet. That's a new project. Free Mars, it's called, in this ERC Consolidator grant. So when we look into continental scale, Europe is our focus of air, rail, bus, primarily competition. We've also been, of course, conscious of the car as an alternative. And I think I don't need to convince you that the situation at the moment is not great. In fact, the European Court of Auditors admits that it's a patchwork of poorly connected national high-speed rail networks. So we don't have a European network. This is how it looks like. You can see the different national lines. So we first had an exercise to see how would possibly unified as in planned in a unified fashion, European network could look like. And we use a series of heuristics to come up with this line design and frequency setting. So you see this is by no means we argue this is the ultimate solution. but I think that does provide a direction here. And this is when we account for the fact that people can also choose for something else to travel by air or by car. So the demand which is distributed is a function of the level of service that you offer in your solution. And we also account for externalities. That means that we assume that there is a central planner which makes decisions also considering, for example, environmental impacts. We don't have here market competition. And in reality, of course, there is. And by that, I mean that we don't have a central planner. And to me, that's what makes this problem interesting compared to classic public transport. So we have lines, we have passenger demand, all these network problems, but there is no central entity which plans the network, not to mention prices. And that goes for air, most obviously, but also for the rail parts. So the network is typically, should be represented and modeled, that's a challenge for the coming years for us, as an outcome of the co-evolution of network designs in market competition settings. What we did already do is look into network evolution, because this picture is maybe, could be your goal, but then the question is how do you work towards it? So we used an evolutionary model to look into which links should be built in any given year, subject to budget constraints. And we had quite a detailed model here about the cost of the infrastructure, tunnels, bridges, all that, based on the topography. And also there is path dependency. That's, I think, an interesting phenomenon here. So you make a cost-benefit analysis, if you wish, for all possible investments in any given year. And it could be that you have a project that now has a low benefits, but once you have you already built certain other links, then it becomes interesting, right? Because it connects to sub-networks, for example, and allow for many new connections. And that's what we see here. So this is the trend in terms of the benefit ratio. And then you can see that there are certain places where there is a peak, because then you all of a sudden it becomes interesting to do something that otherwise was not. And that also translates into certain peaks in the increase in market share for rail year on year. And this is the share of rail. You can see how it increases over this period as a consequence. So there is a detailed demand also model behind that to capture that. And robustness came also in this topic. I think it will gain even additional interest these days with resilience and defense topics in mind. And then if you look at the European network, rail and air, you can see that there is a potential added value in looking also into the combination thereof and the additional robustness that the combination thereof could offer. So that was our point of departure in this last study that I would like to share with you. So what we did here is that we followed this London-Paris example in removing in sequence links from this both rail and air graph, as well as from the joint graph. And first of all, you can see that the air network is much more robust. It's actually hardly something happens until quite a late point. It's a very dense network. This is the loss of performance you can see, or the remaining performance, it's not more than 9%. For the different removal strategies for rail, that is much more dramatic. And it's also, of course, has to do not only with the level of development, so to speak, of a network, but also simply with geometry, which is a result of a cost function that it has as well. So this is much more of a hub-bespoke network, right? And we can also look into the average shortest path length, which is basically the number of transfers or legs one should take. So typically in the air network, that is, we have a lot of direct connections in Europe. Sometimes we need one transfer, very seldom two. Once you remove links, that does change, but takes quite a while to happen. And then it's still sufficiently connected to allow for that. We also looked into the what are the critical nodes and how this looks when you look into rail only versus when you look into rail and air. And we find several clusters, 3 clusters in this regard. And you can see that there's a very different kind of patterns in terms of the impact of their disruption on performance. So that gives you an idea. If you look at these values simply, for these different clusters, they have a very different level, especially the third one, in terms of how vulnerable they are. But all of these values are much greater than these ones. Of course, don't make this one, but you get to a much higher level once you also allow to fall back on air in case of failures in the rail system. So that's a bit where we are now on this topic. It will keep us busy for the coming 5 years for air-rail integration, competition, and the co-evolution of these markets. And if you are interested in any of this work, want to discuss anything else, any ideas you may have, most welcome.